So now we're getting into a different section and a little bit of a calculation section with solution concentrations. Okay, so get those calculators out again. We've learned about a lot of the reactions, right? Precipitation, redox, and whatnot. So we're moving right along. So let's talk a little bit about what is concentration and solution. So again, solution is anything that is with the solute dissolved in the solvent. In our case, we are working with water as the solvent. That's it. So here in this portion, we will be talking really about quantification, is how much of solute are you dissolving in the water? Because we need to know how much of concentration we have, how much of solute we have in there. So we can give concentrations in different units, mass percents, molarity, different kinds of percent solutions also, So this section we will learn only about molarity. Okay, and molarity is moles in a liter of solution. So the moles is of course of the solute in the liter of solution. That's how it goes. Okay, so let's talk a little bit more about this formula that you're going to be working with. So molarity is capital M, which you know in chemistry we have so many M's, right? In mega, micro, milli. So just be careful of your M. Molarity is also M, and moles of solute divided by liters of solution. So here's a short form for it, which you'll be using it because yeah, I'll make you use it a lot. When you make a solution, what do? You weigh a solute. When you calculated how much of solute you need, so you weigh that solute out and then you pour it in the volumetric flask. The volumetric flask is a very accurate instrument for making solutions. You can see it has only one line at the top, and so once you add the solute to it, you add the water until it reaches that line and you make sure everything dissolves. Okay, and so that's how we make solutions in the lab all the time. So when we say that we have a 3 molar solution, what does that mean? A 3 molar solution means that there are 3 moles of sodium chloride in the solution. Okay, 3 molar solution, whether you have 3 liters of it or 5 liters or it doesn't matter, but in per liter, in every 1 liter, you will have 3 moles of NaCl. Okay, so if you want to make a certain amount of solution, like if you want to make a 2 molar solution, let's say of sodium nitrate, and you only want to make 200 milliliters, then what do you need to do? You need to find out the grams, okay, that you're going to need for the sodium nitrate in order to add to that 200 milliliters of water. So for that, we have to do some calculations, okay? And so that's where we're going. Yeah, they're not very hard calculations at all, so keeping it simple, all right? So calculating molarity. So just simple, calculate the molarity of a solution prepared by dissolving 25 grams of potassium iodide into a total volume of 250 milliliters. Now here is the time for me to emphasize the units again, because molarity is moles per liter. So you want to make sure that you change all the units to liters. Okay, now I don't know what your comfort level is with doing conversion factors, but 250 milliliters, you have to divide that by 1,000 in order to get the liters. All right, so you can do it any way you want to, but you need to make sure you convert it. Okay, so I have 2 ways of doing this. Okay, so I'm going to take you both ways and you figure out which one is easier one for you. I'll tell you which one is easy for me. Okay, so the first way that I'm going to take you is through the dimensional analysis. Okay, dimensional analysis is when you set up, right, step by step by step. What do you know? 25 grams. Okay, so you start with that. You don't start with milliliter because you need to calculate the moles, okay, for potassium iodide. So 25 grams of potassium iodide, you convert that into moles. So 166 is the molecular weight of potassium iodide. So you find out the moles that you will need. So 25 grams, and then again you can cross out the units if it makes you feel good. And then what you need to do, now that you have moles of potassium iodide, now you need to divide it by the volume. So you can divide it by 250 milliliters, or you can use 0.25 over here if you want, or you can do this additional setup in which you are actually converting the milliliters to liters. Remember, liters has to be down here, so that's why I put 1000 here. It's not like I'm multiplying 250 by 1000. I'm not doing that, okay? I'm actually dividing 250 by 1000, so that's why the 1000 is up there. Anyhow, once you do the calculation, this is what the molarity is, okay? The other way of doing it is, okay, simpler. Okay, you don't have to set up this way. So I would just go ahead and calculate the moles that I need, which is this many moles of potassium iodide, and then just divide it by the volume. Okay, so which is 0.25 liters, and that's it. That's your answer. Okay, so you use this formula. So sometimes, you know, the dimensional analysis does not really do well. And when you have formulas, you should use formulas because these are, you know, much easier and you will never go wrong, you know, with formulas. Sometimes dimensional analysis, you kind of get lost, like where am I going, you know, with this. So it can be straightforward also. Anyhow, okay, moving along. So you placed 3.92 grams of potassium dichromate in a 100 milliliter volumetric flask. Now you're adding the water to it. What is the molarity? Same kind of question again. Okay, so again, you calculate the moles, all right, for the potassium chromate, 3.92, and the molar mass of potassium chromate is 294. So you divide it by that, and you get 0.133. Moles divided by the volume, you get this. Do you see this, what I've done here for the volume? This is what I do. This is my shortcut, you know, for converting milliliters to liters, all right, is I just multiply it by 10 to the negative 3. Now, this is not an exponent way of writing things, but this is my calculation. So when I put that in the calculator, this is what I do. What happens sometimes is when you're working with numbers, it turns out that you sometimes misplace the zero. Okay, so for example, you want to write this, right? Because that's what's 100 would be divided by 1000. But sometimes you forget and you write this. So then your calculation will all be wrong. Okay, so you don't want to do that. Okay, so be careful. And so for me also, to avoid that, I don't move the decimal point. I just do this as exponent. So if you're good in your calculator, just go ahead and, you know, take the milliliter times, you know, 10 to the negative 3, and you're done. Okay. The bottom part that I have shown you over here, this is a one-step calculation on how to do this. Now it's up to you again how you want to do this. I still like doing step 1, step 2. If you're comfortable, you can do the bottom one, okay, in which case you're just calculating moles on the top. Now see, this is how you calculate moles, right? Generally when I set this up, this is what I do, but look how I've done it over here. Okay, so 3.92 divided by 294 grams. Otherwise you would be setting up like this. So as you get more and more comfortable with doing calculations, you should figure out shorter ways of doing things also. Okay, all right. So here's your final answer. Okay, no matter whether you do it this way or that way, I don't know why I have different answers. I'm going to fix that. But you know, whatever answer it is, it's, you know, it should be all set. So if it's 0.033, this should be 3 over here. I think I've got this wrong here. Okay, I'll fix it. Okay, so then calculating volume. So how many milliliters of water is needed to make 2.5 molar sodium hydroxide from 55 grams of the solid? So how much water is needed? Okay, in this case, you need to make a 2.5 molar solution of sodium hydroxide, and you're making it from 55 grams of sodium hydroxide. So how much water do you need, okay, in this case? So here is again the one strategy, which is the dimensional analysis. Okay, so you start with converting grams to moles of sodium hydroxide. So that's 40 grams is grams per mole is the molecular weight of sodium hydroxide. And then you use the molarity here as your conversion factor. So molarity is what? 2.5 moles over liter. So here I've put moles at the bottom and liter at the top. Why did I do that? Because I need my answer in volume. So I put liters on the top, okay, for that reason. So I'm using this as a conversion factor, although it's a quantity, okay, it's a number, but numbers can be used anyways, right, however you want to use them. So then you convert liters into milliliters because we want the answer in milliliters, okay. So then all you have to do is carry out the calculation. Again, make sure you do the calculation to see that you get the same answer, okay. So here is another way to do things, okay? And as I said, I always teach you, if I can teach you two ways, I will teach you two ways. All right, so here we calculate the moles, okay, for sodium hydroxide. So then you use the formula, okay? So here, once you have the moles, then remember this is your formula, right? So molarity is moles over liter. So molarity is moles over liter. You just found out the moles, you already know the molarity. So now all you need to do is cross multiplication, okay? I find this easier, again, because this is coming from the formula, so it's a lot easier. When I don't have formulas, then I do dimensional analysis, okay? Like in stoichiometry, we do dimensional analysis as much as possible because it's easier. But when you have formulas, it's easier to use formulas, okay? And if you're good with cross multiplication, then go ahead and do this, okay? So molarity, moles over liter, so just do cross multiplication and then you'll get your answer. All right, moving along here. Another one, a solution of sodium chloride used in physiological saline solution has a concentration of 0.165 molar. How many moles are in this solution of 250 milliliters? And then how many grams are also there, okay, in the 250 milliliters of the solution, okay? So first of all, you find the moles, okay, of sodium chloride. I'm going to use this formula here, okay? You need to find the molar mass, of course, of sodium chloride. You will need that. So molarity is moles over liter, so moles is equal to molarity times liter according to cross multiplication. So then you find out the moles of sodium chloride. Pretty easy to do. Once you have the moles, you can always find the grams, okay, just by doing the simple calculation. As I said, not very hard calculations to do, okay? All right. So now let's talk about dilutions. Okay, what we were talking about before was taking a solid and mixing it into water in order to make solutions. But now we're going to deal with dilutions, which means what? It means that you already have a solution made and you're just going to add water to it, okay, in order to dilute it. Okay, so add water. What happens then? The number of solute you have in there remains the same. Okay, so this picture kind of shows you that. If you count the dots, and you don't have to, okay, I will for you. So there are 6 circles in here. If you add water, those 6 circles are still there. So if you think of those 6 circles as the moles, you still have the same moles. You have a different molarity because you have different volume of liquid, but the number of moles is the same, okay, in there. So because of that, we can actually use this formula, okay? So let me show you quickly what we mean by that, all right, how we came up with this formula. So molarity is equal to moles over liters. Moles is equal to molarity times liter. And then I am saying that the moles is the same. So whether you have this moles or this moles, so initial, final, the moles are the same because you have the 6 circles here and the 6 circles here, or solute. So you have that as the same. So which means that moles initial is equal to moles final, which is exactly what I have here. Okay, is that initial molarity and volume is equal to the final molarity and volume, okay, because the number of moles are exactly the same. Okay, so The calculation becomes a lot easier because you don't even need moles in this one. You just need the molarity. You need the molarity of initial solution, or the volume, whatever it is. Okay, since the formula involves four things in there: initial volume, initial molarity, final and final volume and molarity. So it means that I have to give you at least three numbers for you to figure out the fourth one, okay, in there. There are a few things that happen here. First of all, there's only dilution you can do. I mean, you can do the other way too, okay? What does dilution mean again? Dilution means adding of water, right? That's all you're adding over here. It's harder to go from diluted to concentrated, because what do you need to do? You need to remove the water. If you need to remove the water, what do you need to do? Either you evaporate the water or you add more solute to make it more concentrated. Okay, so if you're adding more solute, well, that is not dilution. Dilution is simply adding water. Okay, so keep that in mind. All right, you can only go from a concentrated solution to a dilute solution. Okay, so you can add only water. So I was just thinking like an orange concentrate juice and then adding water to make orange juice, that kind of a thing. That's one thing. The other thing is you still use a volumetric flux, because you're going to start with a certain amount of liquid and then you're going to add water. So again, you're going to start with a certain amount of liquid, and then in the volumetric flask you will add that certain amount of water in order to make that diluted solution. Okay, so I know I'm talking a lot, so let's go ahead and do a problem, because unless you do a problem, we don't understand what's going on. So you can see I have two problems in one page, which means it must be an easy problem, right? Okay, so a saturated stock solution of sodium chloride is 6 molar. How much of this stock solution is needed to prepare 1 liter of physiological saline solution, which was, remember from previous slide, 0.165 molar. Okay, so let me tell you one thing. When you do these problems, okay, these are not hard problems. The only problem that you can have in here is if you don't keep your numbers together. You have to keep your initials together. You have to keep your finals together. Whether you take your final to be initial or initial to be final, it doesn't matter. You need to keep them together on one side of the equal sign, okay? All right, so here it says a saturated stock solution of NaCl is 6 molar. How much of this stock, which means volume, is what you're looking for? So if you decide to give this one M1, then this has to be V1. That's how it's supposed to be then, okay? And then how do you prepare the 1 liter of 0.1? That's your final then, okay? So there are again two ways of doing this, okay? You can either put the numbers first, or you can rearrange your equation first. Whatever you want to do, you do that, okay? So if you were not rearranging your equation first, you would put 6 molar here. V1 is unknown. M final is 0.165, and then V final is 1 liter. You would do that. I like to do this also in some cases. So I isolate what I need, and then I rearrange my equation. So then all I need to do is put in the numbers. Okay, so my MF and VF, the finals are 0.165 and 1 liter, and I will divide all of that by 6 molar solution, and this is what I get. Okay, I get the answer in liters. So I'm just going to go ahead and convert it to milliliters, even though the question didn't ask me, and if it didn't, you don't have to. Okay, I want to just also emphasize that you need to make sure that your units are good. Okay, your units should be in liters, okay, or your units should be in milliliters, depending on what you're calculating. But I would just be on the safe side and put everything on liters. Okay, that's it. So whatever volume you're given, just convert everything to liters. Okay, when you get good at these things, then you know where you can take a shortcut, okay, and what unit you need to change and what you can, get away with not changing. All right, but change for now. Okay, all right. What is the new molarity of a 250 milliliter solution formed from diluting 25 milliliters of a 3.5 molar stock solution? So now the 25 milliliter and the 3.5 are going together. Okay, so here this is the final. Okay, this is the initial. Now Yeah, this is what I did. All right, so MCVC. So here I'm just using C for concentrated and D for diluted. Okay, it's up to you. If you like this one, you use the MI, initial and final. If you like the concentrated or diluted, you use that. If you like ones and twos, you can use that. Okay, that would be M1V1 is equal to M2V2. It's up to you. Okay, honestly, my main thing is you want to put the numbers together, okay, as you want to. So I'm just telling you there are options. Okay, there are options in life. Okay, so the concentrated is, or the diluted one, actually this one should have been on the right hand side. What is the new molarity of a 250 milliliter? So 250 milliliter is the diluted one. Okay, and so the concentrated one is 25 milliliters right here. Oh, and look at this, what I did. I didn't even change the units here. And do you know why I didn't change the units? I didn't change the units because both of them are in milliliters. And I know I'm going to cross that out, so it's not going to matter. Okay, eventually. So I didn't change the units here. So see, I was just telling you that you become, eventually you realize, okay, I don't need to change this because I'm going to cross it out. So 3.5 times 25 milliliters is equal to, what is the new molarity of the 250 ml solution? So here, cross multiplication, so 3.5 divided by 250, right? So here, yeah, I can see that right now that my units are wrong here. So I will correct that, and that's going to be then molarity, right? So that's capital M and not milliliter. So that's 12.5 molarity, okay, in there. So, okay, I think that's that. All right, moving on. So calculating the volume needed, how much water is needed to make 500 milliliters of 2.5 molar solution using 9.5 as a stock solution. So, okay, this problem is just a little bit different, okay, because now it's actually asking how much water we need, okay? It's not asking you for the final volume or the final concentration. It's actually asking you how much water is needed to make this much solution, okay? So, to make a 500 milliliter solution of a 2.5 molar solution using 9.5. So 9.5 is our concentrated stock solution. So that goes over here. Volume we are going to find out. And then 2.5 molar is the final molarity and 500 milliliter is the final volume. And here also you can see that I didn't change the units because then I can get my final answer in milliliters, because if I convert it, I will have to convert it back again, okay, to milliliters. So you can leave it like that because molarity will cross out. So we get this answer. Now this is the volume of what? This is the volume of the stock solution, okay, that you need. How much water do you need though? You're supposed to make 500 milliliters of the solution. So 500 milliliters of the solution minus the stock solution. So this is the amount of water you need. Okay, so again, the 500 is the total amount of solution you need, but the stock solution is giving you 131 milliliters, right? So 131.578 milliliters is coming from the stock solution. So how much water do you need to add? You subtract the two, and this is the amount of water you need to add. Okay, so again, I've written it down here for you. So 368.4 milliliters of water should be added to 131.6 milliliters of stock solution to make the 2.5 molar solution. Okay, that's how you can read this problem. So, because we need to do that. I mean, you can calculate the final molarities and all that, but essentially in the lab, you have to add water, to the stock solution. Okay, so finally, the last thing in this section is concentration of ions, okay? And this is an interesting thing. So we talked about dissociation of ions when we started talking about aqueous reactions. So when you dissolve something, you dissolve an ionic substance, in water, it dissociates. Okay, it dissociates to give you ions. So when you have sodium chloride dissociating to give you Na plus and Cl minus, what does this mean? It means you're getting 1 mole of this and 1 mole of chloride, right? That's what it means. So you have 1 molar, or I should say not 1 molar, 1 mole of sodium chloride giving you 1 mole of sodium ions and then 1 mole of chloride ions. So what does that mean? It means that if you have 1.5 moles molar solution of NaCl, in the end you will still have 1.5 molar sodium ions in there and 1.5 moles of chloride ions in there. Okay, so this is kind of a little bit disorienting to think that, you know, whatever you're starting with, you have the double of those ions. Okay, think about it. The total ions is 3.0. Okay, but the thing is that this is what happens in dissociations. Whatever the concentration of your solution is, that's also going to be the concentration of your ions, okay, in there, if it is a 1-to-1 ratio. So this is the setup, okay? This is kind of what it looks like. So in 1.5 molar NaCl, but you have 1 mole of Na plus ions, sodium ions, in 1 mole of NaCl. So that gives you 1.5 molar sodium ions in there, because sometimes you actually want to know what is the concentration of just the ions, okay, in solution. So this is when you had a 1-to-1 ratio, okay, for everything. So let's see what happens when you have something else. Okay, so find the concentration of species in a 0.25 molar solution of magnesium fluoride. So magnesium fluoride, when it dissociates, you have magnesium and then 2 fluoride ions, okay, in there. So 1 mole, and then you have 1 mole of magnesium ions, and then you have 2 moles of fluoride ions. So if you have 0.25 molar concentration of the initial solution, in the solution then the magnesium is going to be 0.25, but because you have 2 moles of the fluoride, you will have 2 moles, well, 2 times the 0.25, okay, molar solution. And then you add everything up, okay, over here. So which means that you will have a total of 0.5 molar for the fluoride ions. The total concentration is 0.25 and then plus the 0.5, so 0.75. Because 1 molar solution is giving you 3 moles of ions. That's kind of what's happening here. Okay, so that's why you have to kind of remember to multiply by the coefficient, okay, that you get. That's why we go through dissociation, so you understand that it is not F2, it is actually 2F, okay, when you dissociate the ions. You get twice the number of fluorides, because here it's written as F2, so it seems like, oh, it's just 1 F2, but it's not 1 F2, it's 2F, okay, or fluoride. Okay, so find the total concentration of all species in a 2.6 molar solution of strontium phosphate. So here's strontium phosphate. You can dissociate everything. So you get 3 of strontiums and then 2 of phosphates. Now, you don't really have to do major calculations like this one, because hopefully if you understood what's going on here, this is going to become easier. So here's the shorter version, or shorter way of doing this is you calculate you find the total number of ions, and you have 3 of strontium and 2 of phosphate. So which means you have a total of 5 ions in there. So which means that in 2.6 molar solution, you have 5 ions. So you just multiply that by 5, okay, because 1 mole of this is giving you 5 ions. So you can see it's not really very hard calculation to do, but the thing is it's important for you to understand how the dissociation is working. Okay, so if you needed to find out for strontium ion how many strontium ions you would have, you would take 2.6 multiplied by 3, 2.6 multiplied by 2 to get the phosphate ions. Okay, that's all you have to do. Okay, so I guess that's that for this portion. We have one more section to do, but for now, this is it.